This video, we'll finish up our lecture set with a discussion of confidence intervals. First, let's talk about what an interval is. An interval is really just a range of numbers. So when we talk about using an interval, all that we're saying is that rather than giving one value for our guess, we're going to guess a range of values. That is, we're going to guess kind of a start and an end and guess something in between them. So if I'm looking at the average number of insurance claims I'm going to have to file this week, rather than guessing 327, which would be a single number guess or a point estimate, I might say I'll have to file between 300 and 400. Again, a start and an end, 300, 400, and somewhere in between that. Now, because I'm using a range instead of a single number, an interval by its very nature is going to be more accurate than a single number. But it's also going to be less precise. So when I say more accurate, what I mean is there's a higher chance it'll be right. So in terms of the number of insurance claims I'm going to file this week, 327 is very specific. It's very unlikely that's going to be exactly right. But between 300 and 400, it's very likely that that will be true. On the other hand, when I say less precise, that means that 327 is a very specific number that I can make a very specific plan for. But between 300 and 400 is much looser. There's a wide range of possibilities to account for. Now, one way that I can go about making this interval is to start with a guess and then give myself some wiggle room on either side. With the previous example, I might start with a guess of 327 insurance claims. So maybe that's my best guess of what I'm going to have to process this week, or what my hospital is going to have to process this week. And then I'll add a little bit, say 10, to either side. So I start with my best guess, give myself a little wiggle room so that I can be more accurate. If I did this process with this example, I would get an interval of 317 claims to 337 claims by, again, starting with my best guess and then adding a bit of wiggle room to either side. Now, this wiggle room that I just added is completely arbitrary. I just made up that number 10 because I don't know. So rather than adding an arbitrary wiggle room, what we can do is combine the concept of the interval with the population distribution cutoffs for the level of confidence that we had before. So I'm going to use that same population distribution stuff from the central limit theorem that we've been talking about. But now I'm going to take those cutoffs and use those to help me get the wiggle room. This combination gives an interval for my level of confidence. Remember, the cutoffs depend on what my level of confidence is. So I get an interval for the exact level of confidence that I want. And this is called a confidence interval. The components of a confidence interval are the same as the components of a hypothesis test. And I think we actually wrote this out a couple of lecture videos ago, that we simply take the point estimate and subtract the critical value times the standard error. So PE, the point estimate, as before, represents our best guess. So if I'm guessing at the population mean, my best guess is the sample mean. And remember, all of this, the sine qua non is that we have a sample and we're trying to guess at the population. So we have the sample that we can calculate the sample mean for. That's the prerequisite for doing anything involving inferential statistics. Now in this equation expression, everything after the plus minus represents our wiggle room. So all of this stuff over here is the wiggle room, which is formally called the margin of error. This consists of the CV, the critical value or cutoffs from the distribution for the level of confidence. So for my level of confidence, I find the cutoff values, those are my CV, and then the standard error. Remember, that's the standard deviation from the sampling distribution for the mean scores, which just represents that natural variability of the different means calculated with different samples. Recall we had that example of we've got a sample of 100 people, we calculate the mean, a second sample of 100 people, calculate the mean, and because they're different samples, they're going to have slightly different means. That variability between the means, that's the standard error. Now, all of these components are the same as what we had before. We've already looked at point estimates, that's X bar. We've already looked at the critical values. We've already looked at the standard errors. All of this is exactly the same as before. The only thing we're doing is we're combining it in this interval, this reasonable range for the mean. And that's it. Yeah, y'all, that's it. That's all we got. It's the same stuff as before. We combine it with this relatively simple formula, and that gives us, on the scale of our data, the reasonable range that we are blank % confident the population mean falls into. And with that, let's jump into an example, because that really is it. Let's just use the same example as we used earlier, because that'll save us a little work, or you can practice recalculating if you want. Diastolic blood pressure, recall, is the example I worked on after a new diet protocol. So now we're not looking at a difference from a null hypothesis mean or anything like that. Here we're looking to calculate a reasonable range that the mean would fall into. So previously we were looking at the null hypothesis to see if the mean for the patients after the new protocol was the same as before the protocol. Now we're just looking for the reasonable range of diastolic blood pressure for our current patients, the patients after the protocol. And I say patients, it's the population. It's not just the patients I'm studying, it's everybody who would participate in this protocol. So to correspond with our previous alpha of 0.10, we're going to do a 90% confidence interval. And I will say, as a reminder, often we use the alpha levels for error with the hypothesis tests, but with confidence intervals, we often use the percentage of confidence. So we'll call it the term blank % confidence interval is very common, 90% confident, 95% confidence interval. So in this case, we'll do the 90% confidence interval because that's associated, the 90% is associated with the alpha of 0.10. And then here we have our data. So if you'd like the opportunity to go on and practice one, go on and pause the video and give this one a shot, putting this together. Again, the components are the same. We're just putting it together in a bit of a new way. So go on and pause it and give it a shot if you'd like. All right. So the values from earlier. So it's worth noting that all of these values are the same as earlier. Again, we're not doing anything new in terms of these components. We're just putting them together in a different way. Remember how we said it was the hypothesis test. We're putting our data on the scale of the distribution. Here we're putting the distribution on the scale of the data. So we're just kind of putting it together in a different way. So all of these are going to be the same. The X bar, 100.43, same as before. Critical value, plus minus 1.645, same as before. Standard error, sigma over square root of n, same as before, 2.83. For the standard error, we'll say, remember the equation for the basic test statistic, that denominator is the standard error. So that's where this is coming from. I use sigma hat here just to indicate, again, we don't have the population standard deviation. We are just using our sample standard deviation as an estimate. We spoke before, normally that would indicate the use of the t-distribution instead of the normal. In software, it's very easy to go back and forth, but the gains are relatively minimal, so we're just not going to worry about it in this class. All right, so now after I have all of this, I just plug in the values. So I have PE, CV, and SE, and I just plug them into their appropriate places. Yeah, that's really it. So plug in PE, CV, and SE, and hit enter. I do the plus and the minus. So I do the 100.43 plus that quantity on the right, and then 100.43 minus that quantity on the right. Gives me two numbers. The plus is the larger number on the right. The minus is the lower number on the left. And here I have my interval, 95.77 to 105.09. This is the reasonable range of the diastolic blood pressure. So given this, we are 90% confident that the average diastolic blood pressure, recall this is all for the mean average, for the population of patients represented by our sample. So we studied these patients. If they're pretty representative of all of the patients we would see on this protocol, then this is all of the patients for this new dieting protocol. Is between 95.77 and 105.09, which is pretty cool. So we're 90% confident that the average diastolic blood pressure for the population is in here. Now we know, again, we know what the sample one was, but our goal here is not just to make decisions about the sample. We're trying to come up with a range for the population, all the individuals we haven't seen yet, and we're pretty sure their average falls in this range, somewhere in this range. All right, so let's talk through this because sometimes it's easier to see graphically if you're a visual kind of person. So this is kind of where we start from. We start from the standard normal distribution. So here we have the standard normal. It's for that 90% confidence. We've got the cutoffs listed there in blue, the negative 1.64 and the positive 1.64. And this is on the original standard normal distribution scale. Now, remember how we got this. The central limit theorem told us that for groups of sufficient sample size, the distribution of their means was normally distributed. Now, when we do the confidence interval, we convert the cutoffs from the standard normal distribution. So the critical values on the left and the right, the negative 1.64 and the positive 1.64, we convert that to, instead of being on the standard normal scale, we convert that to be on our data scale. In fact, we convert all of the x-axis stuff to be on our data scale. So here's what that looks like. That conversion, you'll see everything in the x-axis is changing, but it represents the same stuff. So that center, which represents the mean of the standard normal, now represents the mean of the data. That -1 represents one standard deviation below the mean of the normal, now still represents one standard deviation below the mean, but now it's one standard deviation below the mean of our data. That +3 on the right-hand side represents 3 standard deviations above the mean in the standard normal. Now it represents 3 standard deviations above the mean in our data now it still represents 3 standard deviations above the mean, but now it's for our data calculated with our mean and our standard deviations. So all we're doing is we're taking the standard normal and we are doing a conversion, just like a Fahrenheit to Celsius conversion or Celsius to Fahrenheit conversion. We are just doing a conversion of this distribution to be on the scale of our data. That's all that's going on with this confidence interval process. The cool part, and the part that we're leaning on the confidence interval for, is that recall how previously we had 90% confidence and we had our kind of cutoff values for our 90% confidence region. Well, now the cool part is not only are we taking the whole distribution and putting it on or could we take the whole distribution and put it on the scale of our data? Now we're taking specifically with the confidence interval formula, we are taking the critical values and putting these critical values on the scale of our data. So these ones are the ones that are really mattering. I'm including all the rest so that you can kind of see what's going on in a broader sense. But normally we only convert these two numbers. We convert the critical values from whatever they were for that particular confidence in the standard normal to be now on the scale of our data. That's the conversion we typically implement. And we only do it for two numbers. You don't have to do it for all these numbers. You don't have to do it for the whole distribution. We just do it for these two numbers because, again, they give us this reasonable range. Now, let's talk about what this says and what this doesn't say. This does not say that 90% of the data are going to fall between 95 and 105, or anything like that. That would imply that this is a distribution of data. It's not. This is, remember, the distribution of means. This says that we're 90% confident that the population mean, or the average of the population, is going to fall in this range. And I can't emphasize enough, this is only valid for group averages, not for individual scores. The biggest reasons are this would have a different standard deviation. Recall here, the standard deviation of the sampling mean is the standard deviation of the original data divided by the square root of n. If we were looking at individual data, this would just be the regular standard deviation. More importantly, and perhaps more to the point, we don't know that the distribution of individual data is normally distributed. With a large enough sample size, we know that the distribution of means for groups is normally distributed from the central limit theorem. But with individual data points, we don't know that. And in fact, it's a very good chance that individual data points are not normally distributed. It's the cool part about the central limit theorem. Even if individual data isn't normally distributed, the means are normally distributed. But that means we can't really do inference with the individual data because we don't know how it's distributed. In any case, this is what's going on graphically with the confidence interval. We're simply taking our standard normal and we're putting the same 90% chunk that we had earlier. We've got the cutoffs earlier, and we're just converting the cutoffs to be on the scale of our data, so that we can say, all right, we're 90% cutoff, 90% confident that the mean for the population of the diastolic blood pressure for patients after implementation, after the new protocol, falls between 95 and 105. So if you took the new protocol, we're 90% confident the mean diastolic blood pressure for the group is between 95 and 105. All right. Well, now why don't you give it a shot? Put together a confidence interval for your earlier problem. So earlier you were doing the age of employees recruited by the new HR manager. Find the 95% confidence interval for the age of the employees. You can grab the values from earlier if you want to, the hypothesis testing example problems, or if you want some more practice, you can practice recalculating them. The critical value for that problem was plus or minus 1.96 for the two sides, the negative and the positive, and the ages are below. So go on and pause the video and give this one a shot. All right, coming back to it. Let's break this down. So I got the sample mean was 30.69. The sample standard deviation was 4.82. And the number of individuals in the sample was 13. My interval was 30.69 plus or minus 1.69, the critical value times sigma over the square root of n. I will note this plus or minus comes from the fact that the critical value is plus or minus. We have two sides of our critical values for that central percentage confidence region. So that's why this is always going to be plus minus, or excuse me, that's why this is plus minus with a symmetric distribution, is because in a symmetric distribution, it's the same number. The top one is just positive, the bottom one is negative. So that's where this comes from. Anyway, plugging this into our Magic Box calculator or Excel, we get 28.07 to 33.31. And this represents the our 95% confidence interval for the age of the population of new employees represented by our sample. So we're 95% confident that the average age for the population is between 28 years old and 33 years old on average. So let's go over again a few of the details regarding interpretation. First of all, again, these are useful for estimating population means and not for making decisions about individuals. The standard deviation for individuals is higher, and the distribution of individuals is unlikely to be normal. It's only normal for the means due to the central limit theorem. So that is a big important thing. I know we've been beating it over the head like crazy, but it's really important for you to remember. The other thing regarding confidence intervals, sometimes we think, hey, we used math to calculate this, and so it's gonna be in there. But remember, confidence intervals are not certain. We'll discuss this in the next slide, but we don't really use 100% confidence intervals. So there's always a chance that something could go wrong, or something could not be in that interval. So this is reflected in our level of confidence, but you need to remember that the true value for the population may and occasionally does lie outside of the interval that we construct with confidence intervals. So it's an important thing to be aware of. Bad ways to use this are to say things like 90% of the data will fall into the interval, which would be incorrect for, among other reasons, because that's talking about individual data points, 90% of the data. And confidence intervals don't describe that. We just say how confident we are that the population mean will fall into that interval. Also, sometimes people say, hey, the mean is in this interval. And remember, we don't know that. We're kind of guessing. It's a percentage confidence thing. Again, we're taking data from a sample and making an educated guess at everybody's mean. And we know different samples give us different guesses. So we're trying to take that into account too. We're combining all this stuff and again, taking an educated guess as to where we think the population mean is with a certain level of confidence. But it's important to realize, again, it's a certain level of confidence that we have. It's not by any means a sure thing. All right. So let's talk about the balance. I mentioned previously we don't use 100% confidence intervals often, and some practitioners wonder why. Well, I guess in both directions. They wonder why we can't make more narrow intervals because they'll be more useful. If only I had more precise information, I could make a better plan or make a more detailed or more clear plan. At the same time, some people want more accurate intervals. Can we just increase the confidence in our interval? I want to be sure that I know what we're talking about. The answer for both of these is yes, we can absolutely increase precision. We can absolutely increase confidence, but these come at the cost of each other. So for instance, my favorite one, can we increase the confidence? Can we have a confidence interval of 100%? The answer is absolutely. We can have a 100% confidence interval. The problem is we lose some interpretability. To have a 100% confidence interval, I'll just tell you your value is between negative infinity and positive infinity. I am 100% confident. That's true. But is that usable? Well, no. It's too imprecise to be really practically usable. Now, on the other hand, if we want it to be really, really, really precise, the kind of end of that is we just give you a single number. That's extraordinarily precise. The problem is that it's wrong, and we know that it's wrong. So we give you increased precision, but now it's just wrong. What's the average age of the new employees? It's 58. Well, it's very precise, and it is not correct. So you have to balance between to what degree do you want this to be correct, and to what degree do you want this to be correct? Or excuse me, to what degree do you want this to be precise, and to what degree do you want this to be correct? And it's it's not always an obvious balance to find. I will say that the balance is not really ours to set. It's an interesting theoretical conversation, and I do like talking about the 100% confidence interval because it is something I get asked from time to time by clients. But the truth is that all of our confidence intervals that we use in applied research are 95%. Is there a good reason for that? Well, it's a reasonable balance between precision and confidence. And that's actually a very good reason. It's a reasonable balance. And it really is a reasonable balance for utility. It's also tradition. We've just been using 95% and alpha equals 0.05 for a very long time. The thing is that if you want to break away from that, it looks suspicious. So let's say I wanted to only do a 90% confidence interval. In that case, it looks like you're trying to hide something. You're not exploring what the data show. You're trying to force them to show what you want them to show. So it's probably not good to break away from this, not because there's something mystical or magical about 95%, but because the reason 95% works well, and the reasons you would break away from this are all probably mostly bad. If you do need to change away from this, make sure you have a rationale and that your reasoning is justifiable. And in that case, just include the justification for those reading the results to evaluate. Because if you change away from this and don't have that, then it's going to look a little bit suspicious. All right. Well, before we sign off today, let's talk through a couple of advanced topics. As we go through the lectures, not every lecture for the rest of the semester, but some of the lecture sets, we'll have a couple of advanced topics that we touch into as they relate. Just to give you an idea of how some of these things are used in practice. This one, I hesitate to call advanced, but it is a cool technique, and it's one we're not going to have time to flesh out more fully in this class. We might have a homework problem on it or two, but it's not going to be a main component. But it's a very cool tie-in between hypothesis testing and confidence intervals, and it's the fact that we can do hypothesis testing with confidence intervals. Ultimately, these both use the same components, the point estimate, the critical value, the standard error. They just combine them in different ways. And because of that, we can't use hypothesis testing to create confidence intervals, but you can use confidence intervals to do hypothesis testing. So to do this, you simply compare your null hypothesis value in the hypothesis test to the confidence interval. If the null hypothesis value is in the confidence interval, then we consider it to be reasonable. Again, confidence interval is the reasonable range. So if the null value is in the reasonable range, then it's reasonable, and we don't reject it. We don't accept it, but we fail to reject it, and we view it as reasonable. However, if the confidence interval is the reasonable range and your null hypothesis is outside the confidence intervals, we would consider the null hypothesis to be outside of the reasonable range and therefore not a particularly reasonable thing. So we would reject the null hypothesis. Again, breaking this down, if the null is in the confidence interval, fail to reject. If it is out of the confidence interval, we reject it. Now, these tests are done at the alpha level of the confidence interval. So if it's a 90% confidence interval, the alpha level is 0.10. If it's a 95% confidence interval, the alpha level for the test is 0.05, etc. And this can be a really cool way to do hypothesis tests. In fact, I'll say that there are some journals who prefer you present confidence intervals because you can do a hypothesis test with a confidence interval if you need to, and confidence intervals give you more information than a hypothesis test does. So confidence intervals, if you have to pick between one or the other, pick a confidence interval, because you can always do a hypothesis test with a confidence interval if you need to, and you can't do make a confidence interval from a hypothesis test. It doesn't go the other way around. So if you have to pick between one or the other, use a confidence interval, and then you can always do your hypothesis testing with it. I will say for the confidence interval, if you had many hypotheses to test about it, you may want to be careful about testing multiple hypotheses. But that's a pretty specific situation, so I don't worry too much about that. Yeah, don't worry too much about that. I shouldn't have said anything. I apologize. But the confidence interval is a pretty cool technique because we can do the hypothesis testing with it. So this second bullet point, again, learn, pay attention. It's something we might have a homework problem on, because it's a pretty cool technique. All right. Well, this one actually is an advanced technique. I debated putting it in here, but there are some advanced statistics that we're not going to have time to talk through in class, and so things like machine learning and some of the fancy data analytics stuff that are very cool. And I'd love to spend more time on, but we're not going to get more time. So the first one of these is called bootstrapping. So this might be something you hear of if you start looking into analytics more, or if you're involved in any way in machine learning algorithms. Ultimately, recall that we used the central limit theorem to make a determination about what the sampling distribution looks like, the equation for it. Bootstrapping is a process to create the sampling distribution from our data, so we don't need the central limit theorem. Now that sounds complicated. It's actually not. It's pretty straightforward. I mentioned bootstrapping for three reasons. One is it's become a popular machine learning method that you might have heard of, but it's not really mystical or even particularly complicated. So it's a good one to dive in on. Bootstrapping has also become pretty modern, or pretty accessible with modern computers. And it's a very handy tool when dealing with individual level data or non-normal data or data with small sample sizes where the central limit theorem can't kick in. Now, when the central limit theorem can kick in, it doesn't really save you all that much, but when it can't kick in, so again, in any of those circumstances I just mentioned, or maybe with big outliers, that would be another time where you'd have to get a massive sample size for the central limit theorem to kick in. In that case, then bootstrapping is very handy because, again, it creates the sampling distribution, and it doesn't require that the sampling distribution has an equation. So again, this sounds very, very fancy. We're not going to discuss too much of the implementation here, but I do want to describe the basic principle and emphasize the approachability of the method because it's very doable. I think it's very straightforward to understand if it's ever that the context of this use pops up in professionally. So what we do in bootstrapping is we take multiple resamples with replacement from the original sample and then calculate the statistic based on it. So if you remember, when I talked about the sampling distribution, about taking a sample of 100 from the population and then calculating the mean, and then taking a separate sample of 100 and then calculating the mean, and then doing it again and calculating the mean, then doing it again and calculating the mean. And we said the sampling distribution was all of those means, and the central limit theorem said the sampling distribution was normally distributed. Bootstrapping says we have 100 participants. I'm going to pick 100 random numbers between 1 and 100, and I can pick the same person twice. So I could pick person 98, and then person 50, and then person 98 again, and then person 49, and then person number 3, and then person number 87. And I'm going to pick 100 numbers between 1 and 100, and I can pick the same people twice or 3 times or 4 times, and then I'm going to use that to calculate a mean. So I've got 100 people in my sample. I calculate 100 numbers, some replacement. I use that to calculate a mean. Then I'm going to pick a new set of 100 random numbers. Again, some people may be selected twice or 3 times, and I'm going to use that to calculate a mean. Those scores to calculate a mean. I'm going to pick a new set of 100 numbers that some people may be repeated. That's called with replacement. Some people may be repeated. I'm going to use that to calculate a mean. So bootstrapping says I'm going to treat those 100 participants from my sample as if they're the population. And I'm going to sample from them with replacement. So that is, some people may be double dipping or triple dipping, and calculate the statistics for them. And then I'm going to make my own graph of all of those means. So I'm going to do it 1,000 times or 10,000 times. And I'm going to make my own graph of what that sampling distribution looks like. So ultimately, it creates the sampling distribution, ultimately uses the sample data as the population distribution of individuals. And it creates the sampling distribution manually. So we can only do this with powerful computers, and any PC that's built after, say, 2015 can probably run one of these algorithms. Maybe after 2010. Powerful computers is relative these days. But in the early 90s, this was not possible to do because we'd have to resample and do this thousands and thousands and thousands of times. But now our computers can do this in the blink of an eye. So this is a very computationally intensive process, but what it lets us do is make our own sampling distributions without any assumptions, except that the original sample matches the population data. In any case, we do that over and over and over again. We create our own custom sampling distribution by physically, manually calculating it. And then we use this to make our determinations, just as we used our sampling distribution before. Again, the cool part is we can do this with individual level data. We can do this with non-normal data. We can do this with data with small sample sizes where the central limit theorem hasn't kicked in, et cetera. Again, central limit theorem works with non-normal data, but only if we have a large enough sample size, 30, 50, 100. This works no matter what your sample size is because you're making a custom sampling distribution and it doesn't have to be normal. And then you can use that equation for that custom sampling distribution or the empirical distribution, the custom sampling distribution to do your calculations. Sounds more complicated than it is. It's just the process of resampling from your people with replacement, calculating the mean, and doing that process thousands of times to get thousands of means to make the sampling distribution graph on your own. And it might look normal. It would look normal if you had a large enough sample size. But if you have a small sample size, then it may or may not. Again, this is computationally intensive, but easily implemented with computers past, say, 2010. As long as the number of resamples you're doing to make that sampling distribution is small enough. So the number of times you grab those samples, you may only do that, I don't know, let's say 10,000 times or less, then that'll run. In any case, that's bootstrapping. That's the concept. And again, we're not going to go into doing this. That's not going to be you're not going to be expected to do that for your homework or anything. But in case you run across it, that's what it is. And it is a very useful technique. So if you run across a data situation with really small sample sizes and crazy distributions of data, this is a good one to remember. And that'll do it for this lecture set. So thanks for sticking with me. This was a long week. I'm sure y'all are pretty tired by this, but this is the foundations of inferential statistics, and we are going to be calling back on the concepts that we learned in this lecture set over and over and over and over again for the rest of class. Hypothesis tests, confidence intervals, critical values, standard errors. These are going to be common terms that just keep appearing over and over and over again. Sampling distributions. So this is stuff to absolutely make sure you take the time to master. If you have to rewatch it, make sure you take the time to get this down, because this stuff is really foundational. This is the fundamental stuff, the fundamental concepts of inferential statistics, our foundations. So in the next video, we'll discuss how we can implement some of this stuff using Excel. So stay with me and check it out.